Devices in a quantum network are connected to each other using three different channels: the quantum channel, the real-time classical channel, and the non-real-time classical channel. Each of these channels can be implemented using optical fiber connections or free space point-to-point laser connections for applications like vehicles or drones or satellites. When optical fibers are used, each channel can be assigned to a separate optical fiber strand, but it's also possible to multiplex multiple of these channels into a single fiber using dense wavelength division multiplexing, or DWDM. I'll describe each of these three channels in more details on the next couple of slides. The first channel that I'll discuss is the quantum channel. This is the channel that carries the actual qubits, which encode the quantum information, typically in the form of individual photons. There are multiple different encoding schemes, including polarization encoding and time-bin encoding, each with their own advantages and disadvantages. Typically, the quantum channel is carried over optical fibers. It's possible to use normal telco fiber that's already in the ground, and it's not necessary to deploy any new type of special fiber for the quantum channel. That said, there are some specific requirements. The main requirement is that the optical path that is used for the quantum channel is not allowed to contain any active components, such as classical routers or classical switches, or even simple classical amplifiers. The technical reason for this is known as the no-cloning theorem. It is, however, allowed to include passive components, such as patch panels or layer 1 optical cross-connects. It is also possible to carry the quantum channel over a free space connection. That free space connection may be a terrestrial point-to-point connection, or it may be a ground station to satellite free space connection. But either way, that free space connection must be implemented as a point-to-point laser. Radio networks such as Wi-Fi networks or cellular networks are currently not suitable for the quantum channel. The second channel is what I call the non-real-time classical channel. This channel is used to carry non-real-time control protocols, management protocols, and orchestration protocols. For management and orchestration, there's a trend towards using YANG, netconf, and restconf. Netconf and restconf are the exact same management protocols that are also used in classical networks. The network management YANG data models are in the process of being adopted to quantum networks, and I'll talk more about that in detail. The control protocols are used to control various aspects of the quantum network. A subset of those control protocols is extremely hard real-time, in the sense that they must be synchronized down to the nanosecond level. And those real-time control protocols have to be carried over a separate channel, which I will discuss on the next slide. But most of the control protocols are not of that hard real-time nature. In the context of quantum secure communications, examples of such non-real-time control protocols include things like key post-processing, specifically information reconciliation or privacy amplification, and key delivery protocols. In the more general context of general-purpose entanglement generating quantum networks, examples of such non-real-time control protocols include things like topology discovery, resource discovery, and the establishment of quantum virtual circuits. These non-real-time control protocols can be carried over the non-real-time classical channel, which is the one shown here, along with orchestration and management protocols. This non-real-time classical channel uses completely normal TCP/IP and Ethernet networks. So you can continue to use your existing classical channel, your existing classical network with routers and switches for this particular channel. The third channel is the real-time classical channel. The real-time classical channel is used to carry that small subset of control protocols that is very hard real-time in nature. As I mentioned in the previous slide, these hard real-time control protocols require extreme precise synchronization down to the nanosecond level. In the context of quantum secure communications, examples of such real-time control protocols include things like clock synchronization, polarization calibration, and key sifting. In the more general context of general-purpose entanglement-based generating quantum networks, examples of such real-time control protocols include things like elementary entanglement generation, entanglement swapping, entanglement purification, teleportation. The diagram at the bottom of this slide shows a concrete example of elementary entanglement generation. In this example, we have a source on the left and a source on the right, and they each generate photons that need to arrive at the thing in the middle, which is called the Bell state analyzer, at exactly the same time down to the nanosecond. That's why we need extremely precise clock synchronization. Also, this entanglement generation protocol is non-deterministic in the sense that multiple attempts are needed to get a successful entanglement. So we need some sort of real-time protocol to report every single photon detector click at the Bell state analyzer back to the sources so that the elementary entanglement generation attempts can be repeated until we finally get a successful entanglement. This requires an enormous volume of control messages, and they need to be very precisely timed. And for that reason, these real-time control protocols typically do not use TCP or not even Ethernet. Instead, these protocols very often use proprietary framing, and they're typically implemented in custom FPGAs. Now, because these protocols use custom framing and not standard Ethernet framing, these hard real-time control protocols have to be carried over a dedicated and separate channel, which I refer to as the real-time classical channel. But there's no standard name for it. It's also known by many other names. If you look at the documentation of some of these products, you'll see terms like the service channel or the synchronization channel. But the main point is that because of this proprietary framing, the optical path for these real-time classical channels is not allowed to contain any IP routers or Ethernet switches, because they won't recognize the proprietary framing. But you are allowed to use DWDM, muxes, or amplifiers, unlike the quantum channel.